What if I told you that the clock on your wall is ticking faster or slower than a clock orbiting Earth right now? It sounds like science fiction, but it's a very real phenomenon. We re-diving into the mind-bending reality of time dilation and microgravity and how being off-world literally changes time itself. Gravity's hidden clock time feels like a metronome, steady, impartial, universal, but the universe keeps a different beat. Time is elastic, not absolute, and it flexes in the presence of motion and mass. This isn't poetry, it's physics. The stronger the gravity, the slower time flows. The faster you move, the slower your clock runs compared to someone at rest. Two effects, two tugs on the same invisible strand. Einstein's audacious idea was that gravity isn't a force tugging from afar at S geometry. Mass and energy warp spacetime, and time is part of that fabric. Imagine laying a grid over the cosmos and watching it bend near stars, planets, even you. A clock closer to a massive body, deeper in the gravitational well, ticks more slowly than one higher up where the spacetime is less curved. Stand on a mountain and you age ever so slightly faster than someone at sea level. Fly fast enough and your seconds stretch thinner than your friends on the ground. Together, these effects give time a texture you can't feel but instruments can catch. The chill comes when you realize that your now is a local dialect, not a universal language. Escaping Earth's time grip, microgravity isn't the absence of gravity. It has the sensation of weightlessness you feel in free fall, like an endless roller coaster drop where you and your spacecraft fall together. The International Space Station ISS experiences microgravity because it's constantly falling toward Earth, missing it due to its high sideways velocity and thus perpetually orbiting. In orbit, two hands pull on time. The ISS is higher than Earth's surface where gravity is weaker, and this makes onboard clocks tick faster. But astronauts also move at breathtaking speed, about 7.7 kilometers per second, and that motion slows their clocks. In low Earth orbit, the speed effect wins. The result, astronauts age a tiny bit more slowly than people on the ground. How tiny? On the ISS, the net difference is around a few dozen microseconds per day, so small you'd never notice it in a mirror. Over a 6-month mission, that adds up to mere milliseconds. Yet it's real and measurable, and it means an astronaut returning home is literally a sliver younger than their twin. The atomic clocks don't lie. If time keeps secrets, atomic clocks pry them open. These devices use the precise frequency of atoms cesium, rubidium, aluminum, ytterbium to keep time with astonishing fidelity. Move them, lift them, launch them, and they tattle on time's subtle shifts. A famous early test flew cesium clocks around the world on commercial airliners. When compared to clocks left on the ground, they disagreed by exactly the amounts relativity predicts. Launch a super-stable hydrogen maser high above Earth and its ticks speed up as gravity relaxes again, exactly as predicted. Today, optical lattice clocks can detect time differences between shelves in the same lab. Raise one clock by a few centimeters and it runs discernible faster. Satellites have turned these quirks into engineering. GPS satellites orbiting far higher than the ISS sit where gravity is weaker, which makes their clocks run faster relative to Earth. But they're also moving fast, which slows them down. The two effects don't cancel. Their clocks would run about 38 microseconds per day faster than ground clocks if left uncorrected. Engineers pre-adjust them and continuously tune the system so your phone can find your location to within meters instead of drifting kilometers per day. On the ISS, the math leans the other way. Higher altitude tries to speed the clock up by a few microseconds per day, while the station's velocity slows it by several times that. The net, slower time in orbit, measured not by feeling but by physics so precise it captures the difference between a heartbeat and a whisper. Beyond the science fiction, real-world impacts, satellite navigation, GPS, Galileo, GLONASS, Beidou signals travel at light speed, but clocks govern everything. If satellite time runs fast or slow by microseconds, your position can drift by kilometers within a day. Relativity isn't a correction tacked on after the fact, it's baked into orbit design, clock settings, and ground control software. Communications and finance, high-frequency trading, power grid synchronization, and global communications rely on nanosecond-level timing. Ground stations trace their lineage to atomic clocks and relativity-aware time scales, so every packet, trade, and phase angle lines up across continents. Deep space navigation, spacecraft venturing to Mars, Jupiter, or beyond rely on exquisitely timed signals. Engineers use time scales defined for the solar system's center of mass and account for gravitational redshift and velocity effects. Without relativistic bookkeeping, trajectories would drift and rendezvous windows would miss. Long-duration missions to Mars and beyond, for crews in transit, time dilation remains tiny but cumulative. More pressing, the finite speed of light imposes a lonely delay minutes to and from Mars that complicates operations and psychology. Still, mission clocks must reconcile on-board time, Earth time, and solar system time so logs, health data, and science remain coherent. Lunar or Martian colonies. Imagine a lunar city with its own local time. Its clocks 1T tick at exactly the same rate as Earth's because of different gravity and motion. Over weeks and months, tiny drifts build. Solutions include defining a lunar time standard synchronized to a reference like International Atomic Time, applying relativistic offsets, and distributing time via local beacons with ground truth updates. The choreography is less about a single true time and more about consistent translation between local and global times. The philosophical chill of relative time, picture an astronaut floating at the cupola window, watching continents sweep by in silence. Down below, billions of lives unfurl at a slightly different rate. Coming home, they carry an odd fact: the person they were on launch day is now a few milliseconds younger than their earthbound peers. It's comic in scale and cosmic in meaning. Relativity fractures the illusion that time is a shared river. Instead, it's a network of streams, each flowing through its own landscape of motion and gravity. Your heartbeat and mine are neighbors, not twins. The present becomes something intimate and local, stitched to where you are and how you move. There's a human ache in that idea. If time is relative, what anchors us? Maybe precisely this, our ability to reconcile differences. We invent standards, share signals, agree on epochs, and build machines to keep our disparate clocks in conversation. Science doesn't flatten our experiences, it translates between them. Understanding time dilation doesn't make the universe colder, it makes it more honest. It tells us that reality is richer than intuition, that precision is a kind of empathy, and that even in microgravity, where everything floats, meaning lands. We learn that now is not a command but a truce negotiated between motion, mass, and mind. And in that truce, we find our place not at the center of time, but aware enough to count the beats we're given, however they bend.